Hello, everybody. So, apologies for not being able to get the technology and the location to work in my favor previously. Sometimes these things happen. So I'm going to send this over as a recorded lecture, and you can view it at any time at your leisure. And I will make sure to give you my contact details in case you have any questions and would like to get in touch. So first, let me introduce myself. My name is Josh Fein-Brown. I'm an osteopath and naturopath, and also graduated from the pain management course in 2021, the first year which it ran. And I've been interested in pain for a very long time, and it was the perfect way to increase my depth of knowledge and to get some really good contacts within the pain world as well. And Roman and Mohammed have been fantastic. So the talk we're going to do today is a talk that summarizes my interests. The dissertation that I wrote for the pain management course was on pain and the role of fear. And the perspective that I took was a perspective that incorporated both evolutionary reasoning and the predictive processing model for perceptions and consciousness. So today's talk is going to summarize how the relationships between fear and pain, and how we can use the predictive processing model to gain a much better understanding of how fear and pain are interlinked. And then I'm going to make some suggestions about how I, in my clinical practice, work with these models to really help patients overcome their fear and their pain. So without further ado, let's get started. So we're going to start at the very beginning of life. So I want you to use your imagination for a moment to try and picture what the world would have been like at the very dawn of biological life. So this was 4 billion years ago. And just to get you an understanding of the difference between 1 million years and 1 billion years, 1 million seconds, just see if you can get an idea of how long 1 million seconds is in your mind. So 1 million seconds is in fact 11 days. 1 billion seconds, however, and this is using the American billion, 1,000 million, billion seconds is 37 years. So this should just give you an indication of how much more time billion years is than 1 million. Now, in the dawn of life, the planet was relatively new. There was a lot of volcanic activity, a lot of lava. There was the oceans. They were in their liquid form, given our unique location in our solar system, the right distance away from the sun. There was a lot of storms, a lot of lightning, and it was quite a tumultuous place, as far as we understand it. And the origin of life, we believe to have happened in the vents, the volcanic vents underneath the ocean. And the reason that we think it came from there was because minerals were spewing up from the lava and from the depths of the earth in just the right concentrations to be able to form amino acids. And at the same time as the minerals coming up, creating this rich chemical environment, you also had heat from the volcanic vents, which were able to catalyze the reactions needed to create new chemicals within this primordial soup. And after a very long period of time, suddenly the chemicals reacted in such a way that they formed, the amino acids coalesced to form basic proteins. And one of these basic proteins that formed around 4 billion years ago was an RNA molecule. And an RNA molecule, which was one single strand of DNA, which was able to code for itself. So it was able to replicate. And this was the first gene. And this first self-replicating protein was the dawn of life as we know it. Now, As time progressed, this RNA molecule joined with many other genes to create more and more complex proteins. Most of the complex proteins that were added were to help this DNA to protect itself and to make sure that it wasn't making very many errors in its process of replication. Now, it took 1.5 billion years, so it took a really long time before this first replicating molecules started to coalesce into multicellular life. And on that journey, that DNA molecule had to be enveloped into a membrane. It managed to get itself inside a fat molecule floating in this primordial soup and created the very first cell. We'll come on to that later because that was an extremely significant difference between just being a protein floating around in a soup to being encased within a membrane. There are some rules that need to be applied to that. But let's just fast forward a little bit. So at 2.5 billion years ago, multicellular life appeared. And the first multicellular life was very simple, sponge-type organisms. And this was the state of affairs for quite a long time. And in only 800 million years, we go from the first sea-dwelling animals to today's diversity of life that we see on Earth. So you can see that the time frames are accelerating and the complexity of organisms is accelerating as the evolutionary process is increasing in speed. Now, if we fast forward to Homo sapiens, we appeared as Homo sapiens. The genus Homo existed before us, but Homo sapiens, as we are existing today, appeared 250,000 years ago. And I think at this point, it's really worth just taking note of what life was like for the first Homo sapiens. We were hunter-gatherers. We were people who were nomadic, living in an ice age where the forests were turning into plains. And in that environment, it's very useful to be able to sacrifice the body type that is designed for climbing trees, for the body type that is erect and able to run for long distances very efficiently, to be able to track and think and plan ahead. Even if you lose your prey, you can still track your prey and chase it down. And in this environment, we thrived not because we had physical strength, but because we had endurance and were very able to regulate our own temperature, which is why we lost all our fur. And we used to hunt by persistence, chasing down prey over miles and miles to the point where they were so exhausted that they couldn't stand up, and we would just go over and kill them very easily and extract a huge number of food, a huge amount of food from that. So we could take down prey that was much larger than ourselves just by being persistent at it. So this was our lifestyle until approximately 11,000 years ago. 11,000 years ago, the first Homo sapiens remained in place and started to take control over nature, started to farm the land. And with this transition, we were able to produce much more food and our population exploded. Fast forward again to the Industrial Revolution, where technology starts to take over the work of man. And our lifestyles change once again. We start having many more people working in factories. Medicine improves drastically. The quality of life for some people goes up and the life expectancy goes up drastically. 50 years ago, we invent technology. The internet comes into being. And once again, we change the way in which we live our lives. Most of us spending a lot of time sitting down in front of a screen at a very fixed distance, with very limited movement capacity and variation. So you can see that the time frames keep getting shorter for drastic, not only biological evolution now, but cultural evolution, which is the same kind of process, but accelerating much faster. So that is the background. Let's move on to pain and fear. So remember I talked about the DNA becoming enveloped within the membrane, forming the first cell. Now, this significant step created a set of rules for the maintenance of life. And these common tasks that these cells have to do are maintain this membrane. They have to maintain their physical body in order to survive. They have to balance fluids and electrolytes across that membrane. They have to detect danger and protect themselves from it by moving away or somehow fighting the danger. And they have to reproduce. They also have to eat, incorporating energy and nutrients to maintain themselves against this tendency towards entropy. And these are still present with us today. Now, as these organisms became more complex, they started to coalesce, these unicellular organisms, and form multicellular organisms. Originally, they coalesced around a central sphere so that they could exchange chemicals within that central sphere so they could communicate with each other. And this communication at the beginning was enough. The space that they diffused their chemicals from one end of the organism across this central encased space to the other end of the organism, because the organisms were very small, it didn't take very much time. It was efficient enough. But as these organisms got bigger, if a cell on one end of the organism detected danger and the cell on the other end of the organism was responsible for moving the organism, diffusion was no longer appropriate because it just took too much time for the first cell to release chemicals and the second cell to pick it up for them to be able to respond to danger and pass on their genes and survive. So as organisms evolved, the very first neurons evolved. And they serve to communicate electronically between a sensor and an effector. And the first neurons were created to form the receptor and to connect it to a muscle. So the first nervous systems were sensing and responding. And with these first nervous systems came nociceptors. Some of the earliest and most basic nervous systems that we know of are the nervous systems within the jellyfish. These are distributed wide neural nets with no central hub, and they have nociceptors. So if you poke a jellyfish very hard with a stick, it will recoil, it will contract its muscles away from that danger, and it will try to move in the opposite direction. And these early reflexes are still present today. The same thing happens if you grab hold of something too hot, you have this same withdrawal reflex. These have been with us for a really long time. Now, if we look at the function of fear, just like pain, they are both protective mechanisms. And pain in particular is designed to maintain the physical integrity of the body. And so pain represents damage or danger to the body. But fear is also trying to protect the organism, but it seems to be much more externally located. So it's detecting threats within our environment or potential threats within our environment and trying to orchestrate our behavior to either avoid or to freeze or to fight, or in an extreme case, to faint. Now, the freezing, which happens pretty much all animals with a nervous system, freeze with the detection of danger. This is incredibly useful because it really helps to avoid detection. Now, our eyes have evolved to see movement. If you've ever tried to spot a bird in a tree, you hear a bird singing and you're trying to search for it in the bushes, you'll know that you only really see that bird once it starts hopping between the branches or flies away. And this is true for all animals with eyes. Eyes developed to detect movement. And in fact, if you paralyze the muscles that move the eye, you become completely blind. There was a girl who once was born without any muscles in the eye, and she learns to use her head, just like birds do, to keep her eyes moving in space in order to make sure that she wasn't blind, because eyes detect movement. Now, when you freeze, you're not moving, much more difficult to detect. If freezing doesn't work and the predator notices you, flight occurs when the predator is at a distance that you can escape from. So when you detect that this is far enough away that you can run, then you run. Fight happens when you detect that this predator either can be overcome, there's a chance that you can actually escape by fighting, and you're at a distance from this predator that you cannot escape from it. Faint is when you're overwhelmed. You detect that there is no way you can survive this threat, and so your whole system goes into shutdown. It's like a mouse playing dead. If a cat has caught the mouse, often the mouse will just completely freeze, play dead, in order to survive. And what happens physiologically is an overactivation of the parasympathetic system. So heart rate drops, blood pressure drops, all of your systems slow down. And this is extremely useful if you were to be cut and were bleeding, for example. You'd be much less likely to bleed out. You have more time to then escape and to get away. So fear has an extremely valuable role in our survival because of these responses. Now, pain, as we said before, it represents threat to the maintenance of the physical state of the body and can be an object to be feared because any threat to survival is an object that can generate fear. And the two systems connect so strongly because they share a lot of the same systems and functions. Their role is both to protect. Now, fear is defined by Vleien and Linton as an anticipatory emotional response to imminent threat. It's adaptive, and learning takes place rapidly with these threats, either through direct experience. You can observe another person who is experiencing threat and learn fear as a result of observation, or you can hear a story that there is a giant fox at the watering hole who has been eating everybody, and you don't want to go to this watering hole because otherwise you're going to die. So verbal responses or instructions can also generate fear responses within us as well. Now, we're talking about fear as an anticipatory mechanism. You anticipate things to be scared of, anticipating threat. So here I think is a good opportunity to bring in the fear avoidance model. Sorry, the predictive processing model. Now, this model, developed by Carl Friston, is an excellent way of understanding how we form perceptions. And what he says is that we as biological organisms are attempting to avoid the tendency of the universe to move towards chaos. So there is this force, entropy, which is moving towards more complexity. So, for example, water tends to evaporate to gas, and in a gaseous state, there is many more ways in which those molecules can be organized in space, and there's much more potential free energy within a gas than there is in a liquid. Now, the way in which biological organisms fight against this tendency to move towards entropy is maintaining homeostasis. Homeo meaning same, stasis meaning state. So we're remaining in a relatively same state in order to make sure that we have this maintenance of our physical body through time in our lifespans. And in order to do this, we need to act in our environments. We need to make sure that we have a good grasp on reality so that we can orientate our actions in space, we can get food, we can incorporate nutrients, we can survive and maintain these physical bodies. Now, in order to act in the world, we need to understand how the world works. And in order to understand how the world works from the brain's perspective, the only thing the brain really has is frequencies of nerve impulses received from our senses. So if light hits our eyes, the light is detected by the rod cells and the cone cells at the back of the eyes, and then it sends specific nerve impulses in an on and off signal of frequency to the back of our brain. The brain only receives frequencies of nerve impulses. It's the same from any of our senses. So if that's the only information that the brain has to go on, how does it manage to understand and generate complex perceptions and actions in the world? Well, the idea is that the brain learns to predict the world, learns to anticipate what is in the world by generating a model within the higher centers of our brain, and uses the sense data, the incoming sensory information that we have from our environments at all times, to update these models, to make sure that these models remain accurate. And let's just contrast that with the current model for a minute. So the current model would state that if we were to catch a ball, the ball would be thrown. Light from the ball would bounce into our eyes. It would travel to the back of our visual cortex, where we would see the ball, and then the brain would process very, very rapidly many different parameters, for example, distance and speed, and then would communicate with the motor cortex to be able to communicate downstream to our muscles in our trunk and in our arm and in our hand to be able to then move to the right location in space in order to then catch that ball. And this is expected to happen all within less than a second that the ball is traveling, if it's traveling fast, towards us. Now, I've seen YouTube videos of a guy with he's a samurai specialist. And there's another man shooting a high-powered BB gun, so a little plastic pellet. And this is shooting the bullet faster than the eye can see. And he manages to cut that bullet with the sword in space. Now, there is just no way in which he is, or we are, when we're catching something or responding quickly, sensing that object, processing that, then responding. There's just not enough time. So what this idea does is it takes away any need to sense before we act. Because what we're doing in the predictive processing model is we are predicting where this ball is going to be in space based upon all of our previous experience with balls moving in space, and using that generative model of the world to act. And then we are because we generate this model and act at the same time, we've already moved our hand to where we expect that ball to be. And then we use the sense data incoming from our eyes to refine that model, update it, going, I expected it to travel to the right, but it's actually traveling slightly more to the left than I anticipated. So now I can correct my hypothesis using that data incoming from my eyes. And that data takes the form of an error, a mismatch between the hypothesis and the incoming sensory information. So this turns sensory information into prediction error between what we hypothesize and what actually is in the world based upon our sensory information. And this happens all the time. So the metaphor that I like to use with this is driving along at night. So you're driving along in a car and you maybe are having a conversation about somebody's pet. And you're driving in the woods, and what you see is a rat running across the road. And so you slam on your brakes. You don't want to run this poor little creature over. But halfway across the road, this rat, you notice, is not running, but it's rolling, which is a bit odd. And the shape of the rat actually isn't quite rat-shaped. It doesn't have a tail, but it actually, it's a leaf that's rolling across the road in the wind. And your perception changes. You first perceived a rat, then you perceive it differently as a leaf, and you carry on driving and think nothing more of it because you just return to the previous conversation. Or maybe you see something in the distance, you're like, is that a face? Is that somebody I know? And you search and you gather more sensory information. You see that person first as somebody you know, and then you notice that they haven't got the right posture, not wearing the right facial expressions, etc. The hypothesis is updated, you recognize it's not somebody you know, you get on with your day. So this generating of a hypothesis and having it updated with your sense data is happening all the time. And I'd like you just to see if you notice it in your everyday, now that I've highlighted it to you, because it's so fascinating watching your world change from one thing to another before your very eyes. And we'll do some of that later. So, you may be wondering how our brains form the perceptions, and how does attention play a role in this? Well, it seems that when we're forming these perceptions, the brain wants to get the best grasp it can on reality, so we can act effectively. So what it does is it tries to understand what is the most precise information that we can use to get a best grasp on this reality. So in a well-lit room that is familiar to you, you can rely quite heavily on the sense data. So your attention can wander down the sense data because it's very precise. There is very clear delineation between objects, and you can navigate very well using that. However, if you're in a blizzard, in an unfamiliar environment, then what your brain is receiving from your senses is very noisy data. It's very unclear, or in the fog, for example. And so, or at night as well, where there's not much light. So what your brain does when it hasn't got very precise sensory data to rely on, it will rely on the predictions, what it expects to be in the environment. And in this way, your attention can wander between the sense data that's incoming from your senses, or it can wander up, but your perceptions can be based upon the higher level processing, the processing that's going on, predicting how the world may be in order to orientate your actions. And so we can form our perceptions almost purely based upon the predictions. And I think this is where people who are really fearful end up, because often they are anticipating a huge amount of danger. If, for example, if you've injured your knee and you've learned that any stairs you're walking up are extremely painful, and so you're anticipating whenever you encounter stairs to be in pain, and they're an object of fear. And so this anticipation is a top-down generated perception. You do perceive fear and you respond with tension, heart rate increase, and guarding of your limbs in order to protect yourself against this perceived threat, without actually sampling the data that's coming in from your knee when you walk up and down those stairs. So your perceptions are weighted towards those predictions as opposed to being weighted towards the actual incoming sense data. And this happens all the time, especially with chronic pain. The people lose their ability to sample their own bodies for accurate data. And so are based almost entirely on what they've learned causes pain. And that forms the predominance of their perception and their actions. They respond as if this was threatening. So I'll show you what you can do as a clinician to help to guide people's predictions. So we can do this really wonderfully with an ambiguous image. So here we have a cat that is on some stairs, and it's ambiguous, right? We don't know whether the cat's walking up or down the stairs. So here we can change the hypothesis for you. So if I say to you that the cat is walking down to you and you're standing at the bottom of the stairs, looking at the image, what do you see? Now I say to you, actually, you are at the top of the stairs and the cat is walking up towards you and you're looking down at the cat. Now what I'm doing is I'm informing the brain and updating the predictions about what this image means, and it changes what you see, weighting your perception. Let's do some more. So if you've seen these images before, then you'll already understand what you're seeing. But if you haven't, then let's take the image on the right there. If I say to you, this is not just a random series of black and white dots, but there's actually a Dalmatian sniffing the floor in the middle of the image. Suddenly, I've generated our hypothesis about what to expect from the environment, and your sense data confirms that prediction. So here is the head, there's the ear, there's the collar, there's the front leg, there's the back leg, and there's the tail. And here is a cow. facing towards you. Here's the nose, here's the eye, the ear, the head, the other eye, and the other ear. Just watch your mind suddenly change what it perceives. So we can experience pain based upon these hypotheses. So you may have heard the story of a builder who steps off a ladder, a nail goes through his foot, and he screams in agony because he can see the nail poking out the top of his boot. They take him to hospital, they have to give him morphine because nothing else will touch the pain. And he's in a huge amount of distress. He's in real pain. And they take his boot off and they notice that the nail has shot straight in between the gaps between his toes. There is no damage to his tissues whatsoever. So he is forming his really real perceptions based upon what he's predicting, based upon the information that he has coming into his senses. But just notice that he's not paying attention to the interoceptive information. He's not paying attention to the information that's actually coming in from his foot, from within his foot. But he's paying and weighting his perceptions towards the visual information that he's seeing. Seeing and the contextual information he's seeing, stepping off a ladder at a building site, that is dominating his perception, not the internal information. So, let's just mention active inference. It's a really key concept with this. Active inference is when our perceptions are not just like a receiving and forming of a sensory thing, but in fact they are folded within the perceptions are actions. So this man who is stepping onto this nail, the actions that he is going to demonstrate as part of this perception are all about protection of that foot. So he's going to avoid loading it. He's going to tense all the muscles in his body. His whole autonomic nervous system is going to respond as if he's under threat. The amount of blood that's pumped around the system is going to change, etc., etc. So this perception is actively inferred onto his body. Or let's take the example of the person who you think you know, your perception is ambiguous there. What do you do in that instance? You look. So the perception of something being ambiguous causes us to move our eyes or move our senses in order to try and gather information that helps us to be accurate and precise with our perceptions. So in the act of not understanding your environment, you actively infer your movements to sample that ambiguous sense data. You move your eyes to try and see more. You turn on a light to try and update your vision. And I imagine this very much like a mouse moving in reverse. So if you ever overloaded an old Microsoft computer, you would have seen the mouse tails that were generated. Now, the perception creates proprioceptive predictions. And I imagine this like that mouse tail, but moving in reverse. So here would be the proprioceptive prediction. And as it's cashed out, as it moves down the efferent towards our muscles then seek to confirm this proprioceptive prediction, much like that mouse moving towards where the prediction is made. And if this is accurate, then that means we have an accurate grasp on the world. Just like if you're moving along the pavement, you're predicting that it's going to be flat. And so you have plenty of architecture available in your brain to think about where you're going to eat for lunch tomorrow, or what that date is going to be in 2 days' time. But suddenly, if your surface is not even anymore, you're walking along and you trip. It's very hard to maintain that internal narrative while you're falling and trying to update your prediction about what the ground was like and move to balance yourself again. So as long as we are predicting, and that prediction is a proprioceptive one that is accurate according to our environment, then we have a seamless relationship with the world. It works. Until the sense data doesn't confirm our predictions and it sends a huge amount of error messages up the system, and then we have to update our hypothesis. And in the process of updating, it requires a huge amount of energy. And so we have to then use our resources in our brain to update those predictions, and it's hard to pay attention to anything else. So in a natural setting, back to our hunter-gatherers again, fear and pain are part of everyday life. You, in order to hunt, have to encounter a chaotic environment that is very dangerous. You may cut yourself on the thorn, you may be attacked by the thing that you're trying to hunt, you may fall down a ditch. There's so many different hazards within this environment that you have to move through. Pain is also a part of everyday life. You haven't got shoes, you're bumping into things all the time, you have to wash in cold water, you're continually exposed to nociceptive stimuli all the time. When I was cycling home, I was noticing my face was, because it was raining and cold, my face was closing up and I was squinting all the time. And this was my face being exposed to that cold sensation. Those nociceptors were firing and they were creating a contracting reflex to try and protect my eyes. And I noticed this and I was able to then relax my eyes and I could suddenly see better. So in the exposure to our environment, we learned that we can modulate and regulate these continuous minor nociceptive inputs. And in a natural setting as well, we cannot just go out and get food. There will be times in which food is scarce. And it just so happens that if food is scarce, let's say you've injured your ankle, you are unable to move to get food for a few days, and your body prioritizes healing of that ankle up to a point. Now, when hunger starts to threaten survival more than the ankle is threatening survival, something really interesting happens. The hunger actually triggers a reaction within the brain, a release of opiates, a release of adrenaline that suppresses in the periaqueductal gray all of the nociceptive information coming from the ankle. So hunger suppresses pain. And hunger suppressing pain is so useful in the survival context. And I believe that any kind of extreme drive that we have for survival, thirst, hunger, temperature regulation, anything that we need to do to maintain homeostasis will take priority at a certain threshold over painful stimuli. But in our environments that we exist in today, we're so comfortable that we're never forced to experience a perturbation to our homeostasis to the point where it suppresses pain. So we are never that hungry. And I think this sensitizes our systems to nociceptive stimuli. We don't have that learned ability to suppress it. So how does this relate to practice? Well, the first thing that we can do in practice is learn that we, with our words, direct our patient's attention. So we are conductors for what the patient is able to pay attention to. So if you're doing a manual therapy intervention and you're chatting about what the patient is going to be doing tomorrow for lunch, the patient's attention is not on what they're doing in terms of if you're moving their hip, for example, but it's on what they're going to have to lunch tomorrow. And because what we pay attention to is what we learn, that patient who's thinking about lunch will learn about what they're having for lunch. They won't learn anything about their hip. So what we can do as clinicians is allow our patients to pay attention inwardly. And the key question to make sure that the patient is starting to actually understand the sense data that's incoming from their body through their nociceptors in a way that is not necessarily threatening, the key question is, what do you feel? Not how do you feel, not does this feel good, not does this feel bad, not is there pain there, or not is this discomfort, but what do you feel? Now, why I'm so specific about this is because this question forces your internal attention. If you ask it to yourself, let me say to you right now, what do you feel in your left toe? what happens to your attention? What happens in your mind? If you really were trying to answer that question, what you would have done is you would have paid attention inwardly to what sensations that were happening in your toe. Then, if you were trying to communicate that with me, you would have had to find language separating out the sensations within the toe into individual words, symbols, and then communicating that. And in the process of doing that, answering that question, what do you feel, you will be learning about your own body. You will be a student of the interoceptive information inside your own body. And when you start to learn about the normal sensations in your body, pressure, stretch, contraction, relaxation, temperature changes, at their most basic level, you start to build a detailed representation in your mind, a much more detailed hypothesis about what is occurring within your own body. And when you're able to sample the body in an accurate way, because you've built a good understanding of what you feel within, it's much harder for you to form hypotheses based upon the predictions. And I see this a lot with chronic pain patients in particular. What's happening is they have a very poor understanding of what is actually going on inside their bodies. They've got a very good understanding of what they need to avoid in their environment in order to prevent pain, but a very poor differentiation of sensations. They can't tell whether it's stretch or pressure. If you ask them what do they feel, they say it's intense or not intense. They'll tell you the location and intensity often, but not anything detailed about the actual sensations. And if there's no detailed information incoming to update their hypotheses, then it's very easy to predict that any sensation incoming from body that is intense is threatening, and therefore act as if it is. So one of the things that we can do as practitioners very easily, just by asking simple questions, do you feel stretch? Do you feel contraction? Do you feel temperature changes? Do you feel pressure? And the key question, as we've stated before, what do you feel? And the second thing we can do is we can change the incoming sense data. It's because we actively infer when we're in pain, threat, and this active inference is cashed out in our musculoskeletal system as tension. The same as fear. Fear is first a freezing response, which is a tension response within our bodies. We can undermine the predictions about how threatening something is by forcing our patients to relax while they're doing movement. So for the patient who's pretty scared of stepping up the stairs, the likelihood is that before they even get to the stairs, they are tensing and protecting all the muscles in their body that they can. They've stopped breathing. They're not moving in a way that's efficient, and they're not moving in a way that disconfirms their prediction that this is going to be painful. So if we can get our patients to completely relax while they're doing movements, then you can update the hypothesis about what's going to happen and create a mismatch between the prediction of threat, which comes with tension, and instead create a prediction of threats that comes with information that goes, well, we're relaxed. That's not what we expected to happen. And in that moment of unexpected input, you update their hypothesis. And especially if somebody is relaxed, most of the time when we're relaxed, we're safe. And so if you want to help update somebody's predictions that a movement is safe, get them to relax during the movements that they're scared of. So that is my concluding message for today. Thank you so much for listening and taking the time to have a look at my presentation. I'm so sorry once again that I wasn't able to deliver it in person. But if you have any questions for me at all, then please feel free to get in touch. My information will be sent out with the email that gives you the link to this talk. So thank you once again so much for joining. I really appreciate it. Take care, and I will see you again soon.